Okay, let's dive right in. We're often faced with these systems of equations that describe how things change over time. But what if you could just look at those equations and, like a crystal ball, see the future? Well, that's exactly what we're going to do. We're going to turn some abstract math into a visual story that can actually predict the long-term behavior of a system.
So this is the big question, right? You've got a system. Maybe it's modeling populations or electrical circuits, anything really. How can you tell, just by looking at the math, if it's all going to eventually settle down to zero? Or maybe blow up and fly off to infinity? Or do something else entirely? That's the puzzle we're here to solve.
And here's how we're going to tackle it. First, we'll look at the crystal ball formula itself, the eigenvalue solution. Then we'll get into the two simplest behaviors, sources and sinks. After that, we'll look at a more interesting case, the unstable saddle point. And to wrap it all up, we'll take everything we've learned and actually turn the math into a picture. All right, section 1. Let's get to the heart of it and look at the core tool that makes all this prediction even possible.
This equation right here, this is our general solution. Now, I know it might look a little intense at first, but it is incredibly powerful. Those V's are the eigenvectors. Think of them as the special directions or highways in our system. And the lambdas, those are the eigenvalues. They tell us what happens along those highways. Are we speeding up or slowing down? The really important part is that little t for time, stuck up there in the exponent with the eigenvalues. That's where the magic happens.
And here's the real kicker. You don't need to get lost in a ton of heavy calculations to see the big picture. Nope. All of that predictive power, it just comes down to one simple thing. Whether those eigenvalues, lambda 1 and lambda 2, are positive or negative. Their signs are literally the secret code to the whole system.
Okay, so let's check out our first two main categories. These happen when both eigenvalues have the same sign, either both positive or both negative. These are the most straightforward cases, and we call them sources and sinks. This slide lays it out perfectly. They're complete opposites. Over on the left, if both of your eigenvalues are positive, you've got a source. Think of it like a fountain just spraying everything outwards. All solutions fly away to infinity. It's totally unstable. But on the right, if both eigenvalues are negative, you get a sink. And yeah, it's just like a drain. Everything gets pulled inwards and all solutions just die out at zero. That makes it a nice, stable system. All right, so what happens when the eigenvalues can't agree? When one is positive and the other one's negative. Well, that's when we get the most dynamic and, honestly, the coolest case, the unstable saddle point. A saddle point is all about this conflict, this tug of war. The negative eigenvalue creates a direction of attraction. It's pulling solutions in along its eigenvector. At the same time, the positive eigenvalue creates a direction of repulsion. It's pushing solutions out along its own eigenvector. And it's this push-pull dynamic that makes the whole thing unstable. Because unless you start perfectly on that incoming line, you're eventually going to get pushed away. So theory is great and all, but let's make this real. For this last section, we're going to take an actual system of equations, we're going to use our new rules to break it down, and then we're going to sketch a complete picture of how it behaves. And here it is. This is our problem. We've got a system defined by this 2x2 matrix. The goal? Figure out what happens to any starting point x as time marches on. Does it go to zero? Does it fly off to infinity? Let's find out. We're going to follow a simple 4-step game plan. First, find the eigenvalues. That'll tell us what kind of system we have. Second, find the eigenvectors to get our key directions. Third, we'll put it all together and build the specific solution. And finally, we'll use all of that info to draw the phase portrait. Okay, step 1, let's do this. We find the characteristic equation for our matrix, solve it, and bam, we get our two eigenvalues. Lambda 1 is 3, and lambda 2 is -1. And look at that. Right away, we know what we're dealing with. One positive, one negative, it's a saddle point. Now for step 2, we calculate the eigenvectors. For our positive eigenvalue 3, we get the vector 1, 2. And for our negative eigenvalue, -1, we get the vector 1, -2. Now, for step 3, we just plug everything we found back into that general formula from the beginning. And look how beautifully this tells the whole story. You've got the first term with e to the positive 3t. That's the part that's going to grow and push things away. And then you have the second term with e to the negative t. That's the part that's going to decay and pull things in. And finally, we draw the picture. Our eigenvector, 1, 2, corresponds to the line y equals 2x. Since its eigenvalue was a positive 3, the arrows on this line point out, away from the origin. The other eigenvector, 1, negative 2, gives us the line y equals negative 2x. Its eigenvalue was negative 1, so the arrows on this line point in. Now, for every other path, they all follow this flow. They get pulled in toward the origin, kind of following that y equals negative 2x line, but then they feel the push from the other direction and get flung away, running parallel to that y equals 2x line.
So there you have it. We've successfully decoded the math and turned eigenvalues into a clear, visual story for predicting a system's future. But we've only talked about the case where the eigenvalues are real and distinct, which leads to a pretty big question, right? What happens when they're repeated? Or what if they're not even real numbers at all? What if they're complex? Well, that opens up a whole new world of spirals and rotations.